Welcome to AI Paper Slop. Today we are looking at a paper called Group-Reflective Self-Distillation for Agentic Reinforcement Learning, or GRFD, by Binbin Zheng and colleagues.
Right, and for all of you training LLM agents out there, this paper is tackling a massive headache.
Yeah, exactly. I mean, if you've ever dealt with credit assignment in multi-turn environments, you know the pain. Reinforcement learning with verifiable rewards, like GRPO, they just suffer from these really sparse trajectory-level rewards.
So true. And the core insight here is that GRSD forces the policy to reflect on its own successes and failures to generate this group-level DO and avoid guide.
Right, and then it uses that capability-aligned guide as privileged context, right? So it redistributes the sparse turn reward into dense turn-level credit assignments.
Exactly, and it does all this without relying on a stronger external model. The result is just, well, state-of-the-art performance on Qwen backbones across multiple benchmarks.
It's honestly a highly efficient loop for agentic self-evolution. So to really appreciate this, let's set the stage. Imagine you're trying to train a language model agent to book a flight for you online.
Oh boy, yeah.
It clicks like 40 different links, gets completely lost on a hotel booking page, accidentally changes the language to Swedish.
Well, as they do, yeah.
Right. But then on step 41, it randomly clicks the right confirmation button and succeeds.
And standard reinforcement learning just looks at that entire messy process and slaps a massive thumbs up on the whole thing.
Exactly. It tells the model to keep doing exactly that.
Which is the exact wall everyone is hitting in agentic RL right now. I mean, when you have a multi-turn task, whether it's web navigation or complex coding, your terminal rewards are just incredibly coarse.
Because the agent interacts for dozens of steps.
Yeah.
But at the very end, the verifier just gives you a binary signal, right?
Yeah.
Success or failure.
Right, which gives us a single trajectory level advantage signal. But as you said with the flight booking, a successful trajectory almost always contains unnecessary detours.
Yeah, and conversely, a failed one might actually have some brilliant intermediate reasoning that just, got derailed by a minor formatting error at the very end.
Exactly. Standard GRPO, so group relative policy optimization, it just entangles all of those individual actions into one monolithic outcome signal.
So you end up giving the exact same positive reward to the brilliant insight on turn 2 and like the completely useless hallucination on turn 10, just because the overall outcome happened to work out.
Which creates a tremendous amount of noise in the optimization process. So prior self-distillation methods tried to fix this by bringing in external help.
Right, methods like SkillSD or STR.
Yeah, they look at these trajectories and attempt to extract hindsight skills, but to do that, they typically rely on stronger external models.
Like using GPT-4.
Right. You might take a massive frontier model and ask it to critique the rollout of your, say, 1.7 billion parameter policy, pulling out rules for the smaller model to learn from.
Wait, but if we use a massive frontier model to critique a tiny 1.7 billion parameter model, isn't that essentially like having a chess grandmaster analyze a total beginner's game?
That's a great way to put it, actually.
Because the grandmaster's advice might be mathematically flawless, but if they tell the beginner to execute some complex 15-move positional squeeze, the beginner can't even process it.
Exactly. The concepts are just totally outside their capability boundary. The student policy simply cannot reproduce the reasoning the teacher is demanding.
So that's the stronger teacher trap.
That's it. When external models produce guidance that exceeds the current policy's capability boundary, the training signal just becomes useless or even detrimental.
Because the smaller model is trying to mimic a reasoning path, it literally lacks the parameters to understand.
Exactly. And furthermore, extracting skills from single trajectories independently captures path-specific noise. The guidance often becomes overly fixated on hyper-specific details of that one single rollout.
Like the specific name of a variable or some quirk of a particular web page, rather than a generalizable behavioral pattern.
Right. So the bottleneck is twofold. First, coarse whole trajectory rewards that don't tell the model which steps were actually good.
And second, if we try to get step-by-step guidance, relying on a smarter teacher backfires because the advice just goes right over the student's head.
Yes. So how do we get the model to coach itself at its own level without just reinforcing its own existing bad habits?
Okay, yeah, that's the million-dollar question. And the authors tackle this with stage A of GRSD, right? Policy-native self-reflection.
Right. The key here is to force the policy to generate its own training data, ensuring the lessons are entirely policy-native.
So after a rollout is verified by the environment, The exact same policy that's being optimized well, specifically a snapshot of it, is prompted to generate a trajectory-level skill reflection.
Exactly. The prompt basically asks it to identify the key turns, explain the fundamental reasons why the trajectory succeeded or failed, and then summarize concrete DO and avoid behaviors.
Ah, so it's reviewing its own game tape.
Yes, exactly like an athlete reviewing their tape.
But wait, if the model is just a novice, its analysis of its own game tape could be completely delusional, right? Or it might think it failed because of the color of a button rather than clicking the wrong link entirely.
That's a very real risk.
So how are they ensuring these self-reflections are actually high quality and, rooted in reality?
Well, they introduce an external fixed judge to grade the tape. In their experiments, they use a DeepSeek V4 flash model operating at temperature 0.
Wait, DeepSeek. But didn't we just establish that relying on a stronger external model is a trap?
I know, it sounds like a contradiction.
Yeah. Aren't we right back in the capability boundary problem?
The crucial distinction here is the modality of the feedback. The DeepSeek judge only ever outputs a scalar reward, just a single number from 0 to 3.
Oh, really? No text?
No text at all. It never generates or revises the reflection or writes the rules. It just gives a thumbs up or thumbs down on the quality of the policy's own self-analysis.
Okay, based on what criteria, though?
4 strict things. First is causal correctness. Did the policy actually identify the turn that caused the outcome? Second is outcome consistency. Third is faithfulness to the actual trajectory history. And fourth is actionability.
Like, is the DO and avoid advice concrete enough to actually use?
Exactly. And then the policy updates its reflection capability using a separate GRPO surrogate loss based on that scalar score.
Okay, I'm tracking now. So the text itself, the actual guidance that the agent will use later, is generated by the agent. So it is guaranteed to be within the agent's vocabulary and reasoning capacity.
Precisely. It pushes the policy to become a better analyst of its own actions without injecting alien reasoning patterns.
The judge is literally just nudging the agent to write better, more grounded self-reflections.
Right. But, even if the policy writes a structurally perfect, highly actionable self-analysis, a single game tape is still inherently noisy.
Yeah, that makes sense. What if the agent succeeded purely by luck? Like, it fumbles around the environment, accidentally triggers the win condition, and then writes this beautifully articulated self-reflection explaining why its random fumbling was actually a masterclass in strategy.
Right, which happens all the time in RL.
Yeah. It's going to write down a completely superstitious DO and avoid list, and we'd just be reinforcing a fluke.
Which is why stage A alone is insufficient. And that's where stage B comes in group-level guidance construction. To filter out that noise, GRSD relies on contrastive grouping.
Contrastive grouping.
For every single prompt in the training batch, the method samples a group of rollouts. They use a group size of 8 in their experiments.
Okay, 8 rollouts.
It takes all the generated reflections from that group and separates them into 2 buckets. Reflections from the successful rollouts, which they call S+, and reflections from the failed rollouts, S-.
So we have a pile of winning reflections and a pile of losing reflections for the exact same task.
Exactly. Then, a stop gradient snapshot of the policy looks at both of these sets simultaneously. It contrasts the S+ bucket against the S- bucket to synthesize a single, compact, group-reflective guidance prompt.
Let's ground this a bit.
Yeah.
The paper highlights an example from the ALFWorld environment that I think illustrates this perfectly. It's a household embodied reasoning task, right? Finding a mug and cooling it.
Yes, let's unpack that ALFWorld example. So in the successful rollouts for this task, the reflections in the S+ bucket all share a very strict logical sequence.
Right.
First, locate the mug, then navigate to the fridge, cool the mug inside the fridge, and finally move to the coffee machine. The synthesis process identifies that this specific sequence is the common denominator of success.
And what's happening in the S- bucket for that exact same task?
Well, the failed reflections show a pattern of recurring errors. In some rollouts, the agent failed to locate the mug entirely. In others, it picked up a bowl instead of a mug and tried to cool that.
Classic AI mistake.
Yeah, or sometimes it just stood in front of the fridge, uselessly opening and closing the door over and over again.
So by contrasting these successes and failures for the exact same prompt, the synthesis process naturally strips away the lucky flukes and the path-specific noise.
Exactly. What emerges is a distinct, highly focused DO and avoid list. Like, DO follow the locate, cool, move sequence, avoid interacting with bowls, and avoid repetitive actions with the fridge door.
Okay, but wait, I have to push back here on the engineering side.
Sure.
If the model is busy generating these elaborate DO and avoid summaries and synthesizing these group reflections during the training loop, doesn't that compute directly compete with the actual task execution training?
It's a fair concern.
Because we are trying to optimize a policy to solve tasks, not to be a summarization engine,
Right.
Optimization interference is a massive headache in RL. Force a model to do two things at once, it usually gets worse at both.
You're totally right, but the authors designed Stage B specifically to bypass that interference. The synthesis step is a completely detached stop gradient construction.
Stop gradient meaning no gradients flow backward through the sampled guidance.
Exactly. The DO and avoid list is just generated and then treated as fixed text. It doesn't back propagate into the policy parameters.
Oh, I see.
Only the reflection generation in Stage A receives any gradients, and even that is tightly controlled. It's supervised by its own separate reflection loss weight.
Which they kept pretty small, right?
Very small, around 0.01. That gentle loss shapes the reflective behavior just enough to make the summaries useful without, cannibalizing the primary task optimization.
Okay, that makes a lot of sense. So we now have this robust, policy-native, contrastively filtered DO and avoid guide. We have the text.
Yes.
But how does this natural language text actually modify the probability distribution of the model's actions? I mean, we have to translate this advice into actual math for credit assignment to solve that sparse reward problem we started with.
And this is where we get to turn-level self-distillation, which bridges the gap between the text and the math. The frozen policy snapshot evaluates the exact same sampled action tokens under two different conditions.
Okay, two conditions.
First, it looks at the action using a standard student context, just the normal prompt and the interaction history up to that turn.
Right, flying blind.
Second, it looks at the same action using a Peter context, where that synthesized DO and avoid guidance is prepended to the history as privileged information.
Ah, so one where the model is flying blind and one where the model has the cheat sheet.
Exactly. And the algorithm calculates the difference in the log likelihood of the action taken under those two conditions. They call this the teacher-student gap.
The teacher-student gap.
Conceptually, it asks a simple question. If I give you the DO and avoid guide, does the mathematical probability of the action you actually took go up or down?
Oh, wow.
Yeah, if the privileged guidance increases the likelihood of an action within a successful trajectory, that is positive evidence that this specific turn was aligned with the principles of success.
Oh, I see how this works. It's almost like an audio equalizer on a mixing board.
Yeah, okay, yeah.
Like the verifier at the very end of the trajectory is the overall volume slider for the track. It determines if the whole song is a hit or a miss. But this teacher-student log likelihood gap acts like the EQ for specific turns.
That captures the dynamic perfectly.
It lets you boost the crisp vocals, the specific good actions, and cut the muddy bass, the specific bad actions, without actually changing the overall volume of the trajectory.
That's a great analogy. And the math reflects that relationship. The evidence from the log likelihood gap is aligned with the verifier's reward, normalized and clipped to create a turn-level modulation score.
So they take the original blunt trajectory level advantage and multiply it by a turn level modifier.
Exactly, which is a combination of a scaling factor and that turn-level score.
So what are the practical implications of structuring the math that way, like multiplying it instead of just replacing it?
It provides a strict mathematical guarantee. Because of how they scale and clip the modulation score, multiplying the advantage by that factor guarantees that the modulation can never flip the sign of the verifier's original ground truth reward.
Oh, that's crucial.
Right. It just sharpens the resolution. It makes a good turn in a successful rollout significantly more rewarding, and a bad turn in a failed rollout significantly more penalized. But it will never take a failed trajectory and accidentally boost an action so much that the advantage becomes positive.
So the external verifier remains the absolute authority on the ultimate direction. The self-distillation just handled the turn-by-turn granularity, which is exactly the balance we need. We trust the verifier to tell us if the flight got booked or not. We just don't trust its resolution on whether step 22 was useful.
Right, exactly.
Okay, so the architecture is elegant, but as an engineer, the real question is whether this actually scales and beats the baselines in practice. What do the empirical results actually look like?
They are remarkably strong. The researchers evaluated GRSD across 3 different model scales to prove it wasn't just, a fluke of a specific size.
Which models?
They used Qwen 3 1.7b, Qwen 2.53b, and Qwen 2.57b.
Okay, solid spread.
And they tested these across 3 very distinct environments. There's ALFWorld, which tests embodied reasoning in text-based homes. There's search-based QA, testing tool-augmented generation, and there's WebShop, testing complex web navigation and e-commerce tasks.
And how did it hold up?
Across the board, GRSD consistently outperforms standard GRPO, general on-policy distillation methods, and those prior skill-based methods we talked about, like SkillSD and SDR.
Let's dig into those ALFWorld results, but the numbers there on the Qwen 2.57b backbone are just wild. It literally hits a 100% success rate on several task categories.
Yeah, perfect success on pick, clean, and look tasks.
Which, to give some context to you listening, a clean task in ALFWorld isn't just a single command. The agent has to navigate through rooms, find a specific object like a cloth or an apple, locate a sink or a basin, interact with the water, clean the object, and then put it somewhere specific.
Right, it's a long sequence.
A 100% success rate on a multi-step sequence like that is a massive claim for a 7B model.
It really is. And hitting 100% across multiple categories highlights how effectively the turn-level credit assignment roots out those single-turn errors that usually derail long trajectories.
What about the ablation studies? Did they find anything interesting there?
Incredible insight there, actually. For example, they looked at the granularity of the modulation itself. They found that turn-level modulation vastly outperforms both token-level and trajectory-level modulation.
Wait, I would have assumed more granularity is always better. Why wouldn't token-level distillation work best?
You'd think so, but token-level is simply too noisy for reinforcement learning. If you evaluate the log likelihood gap for every single token, you end up adjusting the probabilities of grammatical glue words.
Oh, like the, and, or is.
Exactly. Adjusting those based on the DO and avoid guide introduces high-frequency semantic noise that completely destabilizes the optimization process.
That makes total sense. Turn level perfectly captures the actual semantic action the agent is taking without getting lost in the grammar.
Exactly. And trajectory level, as we discussed, just remains too coarse.
What about the contrastive grouping? We talked about the S plus and S minus buckets earlier. What happens if you take away the failed reflections and just synthesize the successes?
Oh, removing the failed reflections, the S minus bucket, causes a significant drop in performance. On WebShop, for instance, removing the failures drops the success rate by nearly 4%.
WebShop is the simulated e-commerce environment. It involves parsing long HTML-like lists, searching and selecting options. I can see why failures matter there. The state space of wrong buttons to click is just massive.
Absolutely massive. And that 4% drop empirically proves that contrasting failures is philosophically essential for RL in these spaces. Knowing exactly what not to do is just as important as knowing what to do.
Right.
The S- bucket explicitly identifies those dead ends and repetitive loops, ensuring the DO and avoid guide has negative constraints. Without it, the agent easily falls back into those traps.
Does all this synthesis mean the model is basically just memorizing the training tasks, though? Like if it's building specific DO and avoid lists for specific prompts, how does it generalize to a task it's never seen?
Generalization is actually one of its strongest empirical outcomes. On the ALFWorld unseen tasks, so environments and objectives, the model was never trained on GRSD, outperformed standard GRPO by 8.2%. Yeah, by internalizing this capability-compatible guidance, the model isn't just memorizing the path to a specific coffee machine, it's learning transferable decision principles, like how to explore a room systematically, or how to verify an object before interacting with it.
Okay, I have to ask the critical engineering question about budget, though.
I figured you would.
We are generating a reflection for every single rollout in Stage A. We are calling an external DeepSeek judge to score those reflections. We are doing a contrastive group-level synthesis step in Stage B, and then we are running an extra teacher forward pass to get the log likelihoods for every action.
It sounds like a lot, yeah.
If this takes 3 times as long to train, a lot of engineering teams are just going to pass, regardless of the performance bump.
It is a completely valid concern, but the authors break down the precise computational cost, and the efficiency is really surprising. GRSD only increases the average wall clock time per policy update by 17% compared to standard GRPO.
Wait, only 17%? With all of those additional LLM calls and forward passes, how are they keeping the overhead that low?
Several optimizations make it feasible. First, The group-level synthesis in Stage B only happens once per prompt, not once per rollout. You're condensing a group of 8 rollouts into a single synthesis call.
Okay, that saves a lot right there.
Second, because they condense the reflections into a very compact, short DO and avoid guide, the extra teacher forward pass is quite fast. In their profiling, the teacher forward pass took only 12 seconds per update.
Wow.
And most importantly, all of these mechanisms, the reflections, the judge, the guidance synthesis, the teacher context, they're completely deactivated during inference.
Oh, yeah.
Yeah, when you deploy the trained policy, you just run it with a standard prompt. It adds absolutely zero overhead at inference time.
A 17% training overhead for a massive performance bump, perfect success rates on complex reasoning tasks, and zero inference latency. I mean, that is a trade-off almost any ML team will take without hesitation.
Absolutely.
It makes this highly practical for real-world post-training deployment, not just some academic curiosity.
It really represents a fundamental shift in how we approach agentic RL. We are moving from simply learning from outcomes to learning from the reasons behind those outcomes, calibrated perfectly to what the model's current parameters can actually understand.
Which leaves us with a truly fascinating forward-looking question to consider. If a relatively small 1.7 billion parameter model can extract highly effective, capability-aligned training signals from its own failures without needing a GPT-4 level teacher to generate its reasoning, are we looking at a scalable pathway to continuous open-ended self-improvement post-deployment?
That's the dream, isn't it?
As our agents enter non-deterministic real-world environments where an omniscient external teacher simply doesn't exist, is policy-native reflection the only viable way forward for true autonomy? Think about it. Thanks for listening to AI Paper Slop. We'll catch you on next deep dive into the research.